Hello everyone, welcome to Engineered. In this today's video, we'll be doing a numerical related to sanitary engineering. And the question is, a certain district of a city has a projected population of 50,000. So P equals to 50,000 residing over an area of 40 hectares, and A equals to 40 hectares. Find the design discharge for the sewer line for the following data. Rate of water supply is given as 200 LPCD, right? And average impermeability coefficient for the entire area, C equals to 0.3. And time of concentration, T equals to 50 minutes, right? So now the sewer line is to be designed for a flow equivalent to wet weather flow, WWF, plus twice the dry weather flow. So this particular design discharge to be calculated is WWF plus 2 times of DWF, right? So we need to find WWF and DWF, right? Now use the British Ministry of Health formula. Assume that 70% of water supply reaches in the sewer as wastewater. So return factor is given as, so here a return factor is given as 70%, that is 0.7, right? And we need to use British Ministry of Health formula, right? So what is British Ministry of Health formula? This one. So this is to calculate I intensity, right? I equals to 760 by T plus 10 for duration of 5 to 20 minutes. That is duration of system 5 to 20 minutes, and I equals to 1020 by T plus 20 for duration of 20 to 100 minutes, right? Now let's calculate let's calculate dry weather flow. So for the dry weather flow, we need to calculate first the water supply quantity, right? So Q of water supply equals to rate of water supply is 200 LPCD and population is 50,000. So 200 into 50,000, right? So this will be liter per day. If you calculate this, let's calculate 200 into 50,000. It will be 1, 2, 3, 4, 5, 6, 7, right? 10 to the power 7 liter per day. If you calculate this into meter cube per second, it will be 10 to the power 7 into 10 to the power minus 3 meter cube per day, and it will be 7 minus 3, it will be 4 meter cube. Now for to calculate per day to per second, it will be 86400 second, right? So it will be, let's calculate, it will be 10 to the power 4, right? This is the 10 to the power 4 divided by 86400. So our answer will be 0.115, right? 0.115 meter cube per second. Now since the return factor is 0.7, 70% of this amount, 70% of this 0.115 meter cube per second will be our dry weather flow, right? So dry weather flow equals to 70% is 0.7 into 0.115. So let's calculate this. 0.7 into 0.115. So it will be 0.8. Sorry. So what was that? 0.0805. 0.0805 meter cube per second, right? Now let's calculate for wet weather flow. So we know wet weather flow is CIA by 360, right? Now for the C average is given as 0.3, and I, we need to calculate I from the British Ministry of Health formula, and IA is given as 40 hectare, right? So now to calculate I equals to, since the storm duration is now assumed as 50 minutes, because we need to calculate for the maximum discharge, and the maximum discharge will be the discharge will be maximum when time of concentration equals time of duration of storm, right? So now we take t equals to 50 minutes. So I equals, so if t is equal to 50 minutes, it will come under this formula, right? So 1020 divided by 50 plus 20. So let's calculate this. 1020 divided by 70, right? So it will be 14.57. 14.57. This will be millimeter per hour. Now WWF equals to C is 0.3 into I is 14.57 into A is 40 hectare, right? So it is the 40 hectare. Now divided by 360, right? So it will be in meter cube per second. Let's calculate this. It's 0.3 into 14.57 into 40 divided by 360. It will be 0.485, 0.486 meter cube per second, right? Now design discharge QD equals to WWF plus 2 times of DWF, right? As we mentioned earlier here, right? Now let's calculate this. 0.486 plus 2 times of 0.0805, right? Let's calculate. 0.486 plus 2 times 0.0805. It will be 0.647. 0.647 meter cube per second, right? So this is the answer. Question number 2. Assuming the surface on which rain falls in the thickly built-up residential district as follows. A is given as 40% of area consists of roofs and pavements, right? C1 equals to 0.80, and the coefficient of impermeability is given as 0.80, and 60% of area is covered with lawns and gardens, whose coefficient of impermeability is 0.20. Now we need to calculate first the coefficient of runoff, right? So in order to calculate the coefficient of runoff, we need to do what? We need to first find out this area, right? So 40, let's assume total area is A. It will be the area A1 equals to 0.40% of A, right? This will be 0.4 A, right? And C1 is given as 0.80. Again here A2 is 0.60 A, right? 60% of A, and C2 is 0.20, right? Now we need to calculate the coefficient of runoff, right? Average coefficient of runoff. Let's say C equals to, it will be C1 A1 plus C2 A2 divided by A1 plus A2, right? So C1 is 0.80 into 0.4A plus 0.20 into 0.6A by 0.4A plus 0.6A, right? So let's calculate this. This will be 0.80 into 0.40 plus 0.20 into 0.6, right? So it will be 0.44A, right? Now in down, it will be in the denominator, it will be 1a, right? So the answer will be the a is cancelled, and so answer will be 0.44. So average coefficient of runoff, the coefficient of runoff will be 0.44, right? So here is the answer. And if the total area of the district is 2 hectares, so area is given as, total area is given as 2 hectares. Now the maximum intensity of rainfall is taken as 50 mm per hour. So I is given as 50 mm per hour, right? So now we need to calculate what? A runoff of the district. So we need to calculate Q. Q is equal to 6 CIA divided by 360, right? So C is 0.44 into I is 50. So into A is 2 by 360. So the one thing is you need, in order to apply this formula, you need to have I in millimeter per hour and A in hectare, right? So these are the units for the for applying this particular formula. Now if you calculate this, okay, let's see, 0.44 into 50 into 2, right? So divide by 360, it will be 0.122, right? So our answer will be 0.122 meter cube per second. So that's the answer. So question number 3, the surface per town on which the rainfall is classified as. The percentage of area and runoff coefficient is given as in the table. So if you add up this will be 100%, right? So 100%. And if you need to, first of all, you need to find out the average coefficient of runoff, right? So in order to find the average coefficient of runoff C, you need to multiply C1A1 plus C2A2, that is summation of CI/AI by summation of AI, right? So we know that summation of AI will be A itself, right? Because 100% of area A equals to let total area be A. In this case, let total area be A. So if you let the total area as A, then the summation of AI will be A itself, right? So in here it will be A only. Now in the upper case, it will be the first one will be area of A1. Here A1 will be 25% of A, that will be 0.25 A, right? Here it will be 0.25 A. Here it will be A2, A3, right? 0.15 A, and here 0.1 A, and here will be 0.2 A and 0.05 A, right? So let's calculate this. 0.80 into particular respective area, right? So 0.25 A plus 0.85 into 0.25 A plus 0.32 into 0.15 A plus 0.20 into 0.1 A plus 0.15 into, let's go up, 0.15 into 0.15 into 0.20 plus 0.05 into 0.20. So if you calculate all of these, let's calculate. So if we calculate all of these, it will be 0.80 into 0.25 plus 0.85 into 0.25 plus 0.32 into 0.15 plus 0.20 into 0.1 plus 0.15 into 0.20 plus 0.20 into 0.05, right? And in the denominator it will be 1. So it will be 0.5205. It will be 0.5205, right? So C is given. Now A is 12 vectors given, right? Here 12 vectors, and time of concentration of the area is TC is given as 15 minutes, right? So from the spell we can calculate I, intensity of rainfall, right? So it will be, for the 15 minutes it will be what? It will be 760 divided by T plus 10, right? For the duration of rainfall duration 5 to 20 minutes, it will be 760 by t plus 10, and for the distance from 20 to 100 it will be 1020 by t plus 20. So if you calculate this 760 by 15 plus 10, it will be, let's calculate this, 760 divided by 15 plus 10, it will be 30.4. 30.4. Now we have this will be in millimeter per hour, right? So C and I and A, okay. Q equals to, so runoff for the catchment equals to CIA by 360 meter cube per second. C is 0.5205 into AI is 30.4 into A is 12 divided by 360. Now let's calculate this. 0.5205 into 30.4 into 12 divided by 360. It will be 0.52774. So 0.527 meter cube per second, right? So this is the answer. Question number 4. The catchment area of the city is 500 hectares. Assuming that the surface on which rain falls is classified as, in the table is given here, and the percentage of area occupying the forest and woodland areas and respective surface is given, and a particular respective runoff coefficient is also given, right? So now, in order to find the runoff coefficient of the area, we need to calculate the average, right? C1A1 plus C2A2 summation of CIAI by summation of AI, right? So in order to do this, there is another method also. If you make a table here, right? So this will be CIAI, right? So, and this will be summation of CIAI. If you multiply the column, this column and this column, it will be summation of CIAI, right? So this is percentage of area, so it will be 10%. So it will be 0.10, right? 0.10, 0.15, 0.20, 0.20, 0.25. Now, if you multiply 0.10 into 0.15, it will be 0.015. And 0.10 into 0.20, it will be 0.02. And 0.15 into 0.15, it will be 0.0225. And 20%, that is 0.20 into 0.25, it will be 0.05. And 20% of A into 0.85, it gives us 0.17. And here it will be 0.225. If you add up all these values, 0.015 plus 0.02 plus 0.0225 plus 0.05 plus 0.17 plus 0.225, it will be 0.5025. 0.5025, right? So it will be CIAI, right? So you can C equals to summation CIAI by summation AI, right? So we have not written A here in each table, right? In each row or the cell. So the summation of AI is A itself, right? So A and A will be cancelled. So coefficient of runoff will itself be 0.5025. 5025. Or you can do according to the previous example, right? So in this way you can also do. Now we have obtained C. Now let's also calculate the quantity of storm water if the area to be solved is A is given as 500 hectares, and time of entry T is given as 15 minutes, and time of flow TF is given as 10 minutes. So what is time of entry and time of flow, right? So if this is the point of concentration, and this is the inlet, and this is the catchment, and this is the most distant place, right? So the time taken by the drop of water from to flow from this distant point of place to this inlet point is time of entry, right? And from the inlet to the point of concentration, it will be time of flow. So time of concentration TC will be T of plus TE, right? So this is the thing. Now we need to calculate coefficient. Sorry, we need to calculate quantity of storm water. So Q equals to what? CIA by 360. But we know TC equals to 15 plus 10, that will be 25 minute. We need to calculate what? I, right? I equals to, so if the TC is 25 minute, for 20 to 100 minute, it will be 1020 by T plus 20, right? So 1020 by T plus 20, sorry, T is 25 plus 20, and it will be what? Let's calculate. 1020 divided by 45, right? So it will be 22.6 mm per hour. So C is 0.5025 into I is 22.6 into A is 500 divided by, sorry, this is 360, right? 360. So if we calculate this, 0.5025 into 22.6 into 500 divided by 360. So it will be 15.77 meter cube per second, right? So that's the answer. Question number 5. Determine the quantity of sewage in meter cube per second for the combined system from the following. So 50% of the area is roofs and pavements. C1 is given as 0.8, and 50% of the area is back and plots. C2 is given as 0.1. So we need to calculate the average coefficient of permeability, right? So C will be, so 50% of the area. So it will be 0.5 into this coefficient of permeability 0.8 plus it will be 50% 0.5 times C2 is 0.1, right? So let's calculate this. 0.5 into 0.8 plus 0.5 into 0.1. So it will be 0.45. 0.4 and 5. Now area is given as 5 hectares and population density is given as 700% per hectare. So it will be, population will be 700 into 5, right? So it will be 3500. Now for the quantity of water supply, it will be water supply rate into this particular population, right? So quantity of water supply, it will be 150 into 3500, right? So it will be, let's calculate, 150 into 3500, it will be 525,000, 525,000 and 0 and 0 liter per day, right? So now peak factor is also given and water supply rate is 150 LPCD, right? Now let's see, let's find the this one. Time of concentration is given as TC equals to 10 minutes. Now first of all, let's calculate weight weather flow, WWF, right? So what is weight weather flow? It will be Q equals to CIA by QW equals to CIA by 360, right? So we have C, we have we do not have I, we have A, right? So we need to calculate first I equals to, for the 10 minutes is 5 to 20 minutes, it will be 760 by T plus what? T plus 10, right? So 760 by T is 10 plus 10. So 760 by 20 we need to calculate, right? So 760 divided by 20, it will be 38. So I equals to 38 millimeter per hour, right? So now C is 0.45, I is 38 and A is 5 by 360. So if we calculate this, it will be 0.45 into 38 into 5, right? So divide by 360. So it will be 0.237 and 5. So we can write 0.238, right? So 0.238 meter cube per second. Now for the dry weather flow, we know what is this? This is quantity of water supply is 525,000 liter per day as calculated before, right? So now, and we know the peak factor is 3, and let's assume return factor as 80%. That will be 0.8, right? So if the return factor is 0.8, then our quantity of sewage will be what? 0.8 times 525,000, right? So let's say our dry weather flow will be 0.8 times 525,000 liter per day. So it will be 0.8 times 525,000. It will be 42 and 4 zeros, right? 1, 2, 3, 4 liter per day. So if we calculate this into meter cube per second, it will be 420 divided by 86400, right? Meter cube per second. Okay. It will be 420 divided by 86400. It will be it's very small, 00486. There been 00486 meter cube per second. Now design discharge will be WWF plus, this is wet weather flow, right? Wet weather flow plus what is the peak factor? Peak factor is 3, right? So 3 times DWF. So WWF is 0.238 plus 3 times 0.00486. Let's calculate this. .2238 plus 3 times 0.00486. It will be 0.25258 meter cube per second, or we may write as 0.253 meter cube per second, right? So what is the answer given here? 0.253 meter cube per second. Question number 6. An impervious area of 20 hectares is to be served by a sewer line. This area is subjected to 3 storms XYZ with equal frequency of occurrence, and the duration of these 3 storms is 20 minutes, 30 minutes, and 35 minutes respectively. Taking the time of concentration equal to 30 minutes, so time of concentration is Tc equals to 30 minutes. Determine the maximum runoff from the each storm. So we need to calculate the maximum runoff from each storm, right? So for the first case, let's say this is the case 1, in which T is greater than Tc, right? T is duration of system 35, and the time of concentration is 30 minutes. So T is greater than Tc. In this case, if you see here, since the duration of the rainfall is more than the time of concentration, the whole area will be contributing to the runoff, right? So if you see here in the 30 minutes, it will be whole area will be contributing in the 30 minutes, right? So if you see here 30 minutes, the whole area is 20 hectares, right? So if you see here, so this is the 30 minute, and still up to the 35 minutes, still up to the duration of rainfall, it will be the same area contributing, right? So the same area will contribute up to the 35 minutes, right? Then after that, the rainfall will stop and it will go on decreasing in this manner. Now in this direction also, from 0 to in this way, straight line, and this will be constant, right? So maximum area contributing here is 20, right? Area is 20 hectares. So maximum area is 20 hectares contributing. Now we know T equals to what? T equals to time of concentration. Now our T equals to 35 minutes, right? Our T will be 35 minutes. So if we have T, we can find out Q, right? So what is Q? So for the Q equals to CI by 360, but we do not have I. So I equals to, for the 35 minutes, it will be 1020 by T plus 20, right? So 1020 by T is 35 and plus 20. It will be, let's calculate, 1020 divided by 55, right? So it will be 18.54. 18.54 mm per hour, right? Now we also know A, so and we have C as well, right? So what is the C here is, so C is taken as, C is 1. So here C is taken as 1, or you can also consider as constant. So equals to 1 into I is 18.54 into what? Is 20 hectares, so divide by 360. 360. So what will be the answer? It will be 1 into 18.54 into 20 divided by 360. It will be 1.03 meter cube per second, right? So this is for the first one. Now for the second one, T equals to TC, right? For the T is equal to TC, if we see here, the time of duration of storm and time of concentration is equal. So at 30 minutes, it will be the area contributing will be this whole area, right? So 20 hectare. So this is the thing. Now here A is 20, right? And T is equal to 30 minutes, and I equals to 1020 by T plus 20. It will be 1020 by 30 plus 20, and it will be 1020 by 1020 divided by 50. It will be 20.4 mm per hour. Now Q equals to CIA by 360. It will be 1 into 20.4 into 20 divided by 360. Let's calculate. 1 into 20.4 into 20 divided by 360. So it will be 1.13 meter cube per second, right? Now for the third one, if T is duration of storm is less than the time of concentration, the whole area will not be contributing to the runoff, right? Because the whole area will not be contributing to the for the maximum drainage or maximum runoff. So now if we see here, the area of contributing at the maximum will be in the proportion to the time and area, right? So T is equal to summation of T by TC equals to A by summation of A. So it will be in the proportion of time, right? proportion of time. Now A equals to what? T by Tc into summation of A. So summation of A is 20. So summation of A means whole area. T is our 20, right? So Tc is 35 and summation of A is 20. So if you calculate this will be 20 into 20 divided by 35. So it will be 11.42. So 11.42 will be the area. Sorry. So time of concentration is not 35, right? So there is some mistake. So here it will be 30. Time of concentration is not 35, it is 30. So let's calculate again. 20 into 20 divided by 30. It will be 13.33. Now A is unknown, so 13.33 around here in 20 minutes, right? So it will be around in 20 minutes. So 20 minutes 13.33 here, and it will go up to 13.33 up to 30, and it will come downward, right? Now I equals to we know T is equal to, so T is equal to 20, I equals to, so if it is 20 it will be 760 by T plus 10, right? So 760 by T is 20 plus 10. So it will be 760 by 30, right? It will be 25.33. 25.33. Now Q equals to Ci by 360. C is taken as 1 and I is taken as I is here, we calculated here 25.33, and A is 13.33 divided by 360. So let's calculate this. 1 into 25.33 into 13.33 divided by 360 with 0.938. 0.938 meter cube per second, right? So this is 0.938, this is 1.13, and this is 1.03 meter cube per second. So let's compare this one. So we have, let's write here, for T is greater than Tc, it will be what? 1.03, and when T is equal to Tc, it will be what? 1.13, and if T is less than Tc, it will be 0.938. 0.938, right? So the maximum discharge, maximum runoff is given when T is equals to Tc. So you need to remember this. When the duration of storm is equal to the time of concentration, maximum there will be maximum runoff, right? So maximum runoff occurs when duration of storm is equal to the time of concentration. This is the important point. Okay, that's all for now. Thank you for watching.